everyone. Today I'm going to be talking about physical computing with microbits. My name is Holly Graffam and I'm an MLTI ambassador, and here is my contact information. You should know in the description area of this video there will be a link to a PDF of this slide deck, and you'll be able to click on these links here as well as any other links that are embedded in the slide deck. So, what is physical computing? Physical computing involves interacting with a physical world in addition to a screen. You take data from light, motion, or temperature sensors and control devices such as motors, speakers, and lights. And here is an example of some code that was written for this self-watering microbit project. So what is a microbit? And I'm going to be talking about version 2. I'll point out specifically the advantages of getting version 2. But it is a 4 centimeter by 5 centimeters, so it's pretty small. It's less than the size of a credit card. It's a microcomputer that allows software and hardware to work together. It has an internal processor that it uses. It also has internal LED lights. It has buttons that you can push as inputs. It has sensors such as temperature and light, and many other input and output features that I will go into more detail with later on in this slide deck. And when you program these input and output features, it lets the microbit interact with the physical world. The microbit can also be used to connect to external input and output components, and this really just enhances its programming capabilities. So what are the built-in microbit components? Within the microbit, it has 4 ways that you can activate it through what we would call buttons. There is an A button, a B button. You can press A and B together. And then the 4th button would be the touch logo. It has 25 LED lights that are actually inputs and outputs. You can program it to light up like this. So that would be an output, but they also can be programmed to be light sensors. So that would be the input piece. There is on the new version, so just to back up a little bit, the touch logo was not on the original version, so that is new. And also on version 2 is a microphone. And so on the front of the microbit, you'll see when the little microphone symbol's lit up, that means that you're activating the sound sensor. So it has a radio antenna. There's a way to program this to use Bluetooth. Like I said, it has a microphone, which is new. It has a reset power button. So previously it was just resetting, but now you can power down the microbit using this reset button. There's a way to, the microbit needs power, right? So there is a battery socket, and you can connect you can connect 9 volts, you can connect 4 AAA batteries, you can connect 2 AAA batteries. That's kind of the standard. It really just depends on how much power that you need. When you do connect the battery, it has the standard 2 AAA batteries. It has a 3 volt power on on the pins, and we'll talk a little bit more about the pins down here. These pins 0, 1, and 2, these can all be programmed, and usually you connect external components to that, inputs and outputs. But then, like I said, there is some power. So this pin gives you 3 volts of power, and then this is your ground pin. There is a speaker on here, so you can make sound, music, or other types of buzzers and that type of sound. There are there's also a compass and an accelerometer. So one of the other things that you can do to activate this beyond just these buttons to start the program, you can also use movement like shaking or movement of the microbit, and that will also you can program that to also start the program. So it has a lot of stuff in this tiny, tiny little microcomputer. So I talked about the fact that beyond just all the great things it has internally within it, you can connect, and this is just a small sampling of the things that you can program and connect to the microbit. And you usually make those connections through alligator clips. Sometimes you need jump wires if you're going to use the servo motors. But typically you use the alligator clips. You might use these little LED bulbs that we, are familiar with. You could program this to be with pressure sensors. So when force is added or removed, it activates something in the microbit to do something. You can do wearables with the microbit because it's so small and lightweight. It's easy to think of wearables with this, and these are sewable LEDs. You can see on the ends of each of these, it has a place that you can sew these in like a button. You can make your own switches, if you will, the on-off switches with copper tape and tinfoil. You can use fruit. Think about, the old science experiments with potatoes and lighting up the light bulb. That's kind of the same concept. There are servo motors or other small hobby style motors that you can use to connect to it. You can hack into headphones with the sound, and I said internally on the microbit, there's a light sensor. You can also use this photocell resistor. The light sensor, I'll talk a little bit about analog and digital inputs, and then the complexity in programming them. So the photocell resistor is really it's either on or off, and so sometimes that's easier for students to use. So this is just a small little bit of things that you can add to the microbit. So when you are writing a program that is going to be downloaded onto the microbit through a USB cable that comes with the microbit, you can use Microsoft has a online open source editor called MakeCode, and this works on PCs, Macs, and Chromebooks. It's all web-based, and this kind of looks very familiar if you've done any Scratch. So the MakeCode programming platform can be block programming, which is typically where students start out. And within each of these are called drawers, and within each of these drawers there are multiple blocks that students can use in their block. Or you'll notice right up here, you could switch this over to JavaScript. So if you have some students who are more advanced programmers and they really want to use more of a typical language, if you will, they could use JavaScript. It has this emulator, which you can test your programs on by running that program. And if you in your program you say you're going to program one of these pins, you've attached an LED bulb to it, and so your part of your pin programming is, when something happens with this pin, you're going to the LED bulb will light up. That when you do that programming, it will automatically show that the external components have been programmed. And then you have this workspace over here to actually write your programs. When I teach computer science, and this is not just me, but this is part of, so just to give you a little bit of background with me and the microbits, I did some training through um, I don't know if you call it a curriculum, a corporation called Project Lead the Way. And they really teach computer science K-12, and they offer a lot of different professional development. And one of the options was physical computing and using the microbits. And so I did a week-long training at Worcester Polytech around this. And embedded in their curriculum around computer science is the idea of pair programming. But if you also look at other programming curriculums like code.org, which is where this video comes from, they also recognize pair programming, because what we're trying to get to the idea is that this is, and this is kind of where the problem solving and all of those pieces come in, is that software engineers and programmers, they don't usually work by themselves. They work as part of a team. And so we're trying to foster that collaborative experience by pairing students up. And we call those partners drivers and navigators. And the driver works on the computer downloading and modifying the code. And then the navigator would be the one who will be wiring up the microcontroller to the sensors and coaching the coding. So often we talk about how two heads are better than one. And sometimes it's easy to get lost in the coding piece, and it's great to have a second set of eyeballs and thinking on the coding. And plus, it allows for the building piece, as you'll see, with the circuitry and adding all of the different sensors that they have to do with the physical piece of the microbit. It allows one person to really concentrate on that while the other person is writing the code. And then the idea being that each work session, the roles are changed so that students have the opportunity to be drivers and navigators. I am going to suggest a process of scaffolding the coding and the circuitry skills. I've taught this probably 4 or 5 years, and I've really I've honed in and really solidified my process with this through a little bit of trial and error, my own little iteration, if you will. So this is what I have found is the most advantageous with working with students and the microbits. So the first thing we do is we practice writing some simple code with the emulator. Yeah, this doesn't usually take very long, one day. This is more of a I might show them 1 or 2 things, have 1 or 2 activities that they're required to do, and then it's explore the different drawers, get a feel of the microbit, look at the different blocks, and try to Again, if you've had kids who have any experience with Scratch, they'll start seeing some similarities between the two, and really just talking about uh, getting familiar with the coding and the emulator. So then step two, I we practice coding the internal microbit inputs and outputs, and again making sure that students are always testing the code with the emulator to see if the code needs debugging. Um, Kind of the next step, if you will. But this time we're gonna actually start hooking the microbit, but we're not gonna build out the circuitry pieces of the microbit. So we might do some lessons where they make the LED lights come up. I'll have them have work with all the different buttons and the touch logo, the speaker. We'll do some activities with the shaking of the movement, the microphone, the light sensor, the temperature, and the compass. So what I'm really doing is building some skill set around all of the internal pieces that they're probably going to need to know how to do when it comes time to putting this together in a project that's going to solve a problem. And then it's time to start practicing with the external inputs and outputs. And this is where things can get a little bit more complicated because now you're not just programming. Now you are kind of doing some circuitry work and you're building things. Sometimes it's as simple as programming so that LED bulbs go off, and you can see that here's a picture of a student who developed a program with an LED. Can't really tell, but this student right here had a speaker that they programmed so that when they pressed a button, a tune came out of loosely, when you know what I mean by tune. Although you can program, there is differentiation. It's not just one tone. There is like middle C, D, E. So you can get tunes out of this. And then this one, they did the photocell resistor here. And when it detected light, this is kind of an on-off thing. So when it detected light, the microbit had a certain arrow. We also practice with the little LEDs, the syllables. We'll make some of our own on-off switches with copper tape and aluminum foil. You can also work with other conductive material. I have conductive thread. I've not tried working with conductive paint, but I have conductive thread that that we sometimes need to use. And then the servo motors. And I just want to give a little cautionary tale about the servo motors because I did have a teacher reach out to me about the servo motors. They can be a little finicky. They're not difficult to program, but sometimes the motor itself can be a little finicky, and usually 3 volts is not enough power to really do what you want to do with the servos. So lots of times you need to have like a bigger battery pack that has like that you can put like 4 batteries in. You Servo is just like one type of motor. We like those because you can connect a little arm to it and do some different things. But you could look at other types of motors as well. So here's a couple other tips. So usually I cover 2 to 3 of the inputs and outputs in a typical class period. So, and again, switching back and forth between Navigator. So I'm just going to go back here a little bit. Let's say the first day is the LED lights and the speaker. And then we're going to talk about the buttons and the touch logo. That I might cover all of those in one class, but it might be 4 3 or 4 different tasks. And so task 1, student A would be the navigator, student B would be the driver. Task 2, student B would be the navigator, student A would be the driver. You see where I'm going with this. And so throughout this process, at some point in time, everybody's had ample opportunity to be a navigator and a driver. Some of the sensors. So when you let me go forward here. So some of the sensors can take longer to code, and those are typically your analog inputs, like light sensors and pressure sensors. And so an analog input just means that there isn't like an on off. So with for instance, with a button, you either press it on or it's not pressed and it's off. With the photocell resistor that we add on, it's either receiving light or it's covered and it's not receiving light. But the light sensor on the microbit or adding in the external pressure sensors, there's a range, right? Pressure and light's not consistent, pressure's not consistent. And so you have to do some additional programming to determine like what that range is for whatever the sensor is and whatever the light situation. And the light sensors can be really, really sensitive. Like in the classroom, I will have different students in the same class based on how close they are, say, to the window. What their off level is on the light sensor can be very different than another student. So that usually takes that might take a whole class period to just do those kinds of sensors, because there is a lot of there's a lot of iteration and trying to determine what your range is on those. And then I usually, and I've talked about reflection slides and other slide decks and other presentations that I've talked about, but I use reflection slides. I've really found, particularly in my case where I only saw students once a week, or sometimes I might see them twice in a week. Finding using these reflection slides really gave me the evidence that I needed to make sure students were on track and that they were, accomplishing everything that they needed to accomplish, and just for self-reflection with themselves. So I have them do one of these for each input and output. So not even every not just for the day, but each one of these. So even if we're doing 3 inputs or outputs in a class period, I'll have them do a reflection slide for each one and show me photo evidence that they actually figured out how to program whatever it is that we're going to be programming. And sometimes kids will give me, you'll see, I've shown you some, the photos that I showed you in the earlier slides were taken directly from students' reflection slides. So sometimes, and if we go back and look, they take a picture of like what's actually happened, but then in this case of the compass, a student just took a screenshot of the code itself. So bringing in the design process. Once students have really learned how to use the microbit and all the different components that they can add to it, and then I really dive into the engineering design process. And if you haven't done anything with it before in classes, I have done in many of the previous presentations I've done, I've talked about using the engineering design process in class. And so you kind of have to decide how much of that, how much review that you need to do with that, depending on where you are with these students. But in this case, I'm going to talk about engineering design because they're going to build something to solve a problem. But I think it goes without saying that you could also use the design thinking piece around this, because we're actually kind of using engineering design and design thinking, because we're really talking about the empathy piece and some of the examples I'm going to give you. But there's also oodles of science experiments that you can use with the microbit. So maybe you're going to really use the scientific inquiry approach as opposed to the engineering design process. So here are some project examples. And it's best to give students an open-ended problem or scenario that uses the microbit to solve the problem or build a prototype, such as someone's trying to read your diary. How can you use a microbit to alert you when this is happening? And this is called my Secrets and Safes project, or protecting an object. And this is an image of one of the students was their secret and safe. So this is a pizza box. So when the box was opened, the light went off, and there was actually they had to have more than one output. So there was actually a buzzer in here that you can't, that's out of the picture, but that's what they built. But I've also done interactive art installation, and this was more of a prototype, because obviously we're not going to build a full-scale art installation, but I worked with the art teacher with some of the art that they were creating, and then how can you take that artwork and adapt it so that it could be interactive, so that when, think about like going to a children's museum, those are really lots of times art installations that students somehow interact with. And so how can you use the microbit to do that? And it might, usually that has to do with maybe the light twirls it around, or using the buttons, and when you press the button, something happens, that type of thing. You need to run with your dog after dark, but your mom is worried about you not being seen. How can you make your pet yourself visible when walking at night and using microbit? So this is really gets into some wearable technology that that students can do. And then the plants in the classroom aren't doing so well. It appears they need to be watered over the weekend using a microbit. Can you build a self-watering system? So if you in the very first slide, we saw a project where you can build a using the microbit. You can build a self-watering plant system, and those are just some ones that I have done. That, the sky's the limit when doing different projects. One of the things, and if you've I talk about going through the engineering design process, and students may need help with the constraints of the product. So this is often for myself. We talk about it as a class, but usually I give them what the constraints are. But you certainly could co-create them as a class. But at this point, unless they've had a lot of experience with engineering design and talking about the constraints, usually this is something that you work on together, or you just go ahead and give them to them. And the constraints are often dictated by time, how much time they have to create this product, space, how big can it be, and the materials that you have available. But there could be other things. I've often indicated that they had to have a certain number of inputs and outputs, that it had to somehow respond to the environment. So that's like light, sound, motion, something like that. That the user can activate and deactivate the device as needed, so that it doesn't just run on a continual loop. It needs to be able to be like kind of be able to be off and then activated in some way, in scale. So prototype building. Again, I have talked about these in previous slide decks, but when I'm using, whenever I'm using the engineering design process, I usually include an engineering notebook and reflection slides. So, similar to the reflection slides that I do as students are building their skills around the microbits, I use a similar reflection slide that they fill out daily as they are working on their project. And also, I have an engineering notebook where this follows the engineering design process. So there's a slide in there for identifying problems. There's a slide in there for constraints. As you go through each of the processes, I have a slide deck that students have to complete. The reason that I do both of these is because often the engineering notebook, it doesn't follow like a day-to-day type of thing. You really probably do steps 1 through 4 in one day. Um, and then it might take a lot longer to do the iteration step, and you usually give them multiple slides so that they can include photo evidence or video evidence of each iteration that they're doing. So I find that having a combination, something that is the complete project, and this is usually what I use for assessment, and you can go back in the one of the previous presentations I've done about the engineering design process, and when I talk about assessments and that, if you want to review what that, I'm not going to really get too deeply into that, but the engineering design notebook itself is one of the things that I use for assessment, and then the reflection slides I use as kind of a formative assessment to make sure that students are staying on track. And that's what I've found has been really helpful for me, to be able to look quickly at the reflection slides to see where students are, and if they're questions or concerns and all of that. I so I talked about the make coding space and with the JavaScript, but Microbits has really upped their game, and they now offer other places that you can code using the microbit. So if you don't want to teach your students a new block programming, you can use microbits with Scratch. You can use it with Python if you really want to teach a more traditional programming language. You can use it if you have MacBooks. You can use this with Swift Playground. So and then they also have a couple apps that you can get in the App Store for Apple or Google Play, and be able to get those on your mobile devices so that you can do some of the make coding. The mobile pieces are a little bit more complicated. You have to be able to use Bluetooth, because obviously there's no way to download the file that you make online in the web onto. You physically have to download the programs that you write on the web based in either make code or one of these other coding. You have to download that through the USB onto the actual microbit. So as you saw, the microbit is not attached permanently to your computer. You give it some sort of battery power through a battery pack, and then the program is actually on the microbit itself and runs independently of a computer. So I personally think that even if you're using Scratch and it's easy to default back to using Scratch with this. I also think it's great to teach them even if it's another block programming language, and have them, we've talked a little bit about transferring of skills. Uh, it's great for them to be able to see the similarities and the differences and be able to start transferring those skills in multiple ways. Uh, the number one-stop shop for Microbit tutorials, curriculum, and much more is microbit.org. And I'm going to just show you a little bit of this website. Um, it has how you can get started. Uh, it has lessons. Let's code. It has project ideas. There are video tutorials on all of these different pieces. Really, this is like your one-stop shop to get started with microbits. And so I really recommend that you do a thorough investigation with this in your microbit before you get started using these in the classroom. And these, some of these tutorials are things that you can obviously use right in your classroom. Microbit has this new kind of exciting thing called Microbit Classroom, and there's a whole video here that talks a little bit about it, and it's kind of Google Classroom meets Microbits, if you will, but it's just about I'm going to stop this. It's all about managing the microbit lessons that you give students, and you can actually give them starter code, and you can visually see where they are on that starter code. It's a pretty great concept. So that's something to check out as you look to introduce microbit. And so our friends at MIT that have brought us Scratch, and they have also brought the App Inventor. If you've not looked at their App Inventor, that is another great tool that they offer, open source. So they got on the microbit bandwagon, if you will, and they developed a curriculum called How to Train Your Robot, and it is a 1 week of activities that really talk about artificial intelligence. So you're going to actually use the microbit to build a robot, if you will. So that is a great that's another great curriculum. There's some of these others are like Steam Studio. This has a curriculum that you can follow. MakerEd. So these are really like I don't know. I don't want to build my own steps of scaffolding. I really just want to have the curriculum all laid out for me. And so these are some great options. Microbit for Mad Scientists. This is a book that you can get on Amazon, and it has a lot of science experiments that you can do. Also on here, this resource, the microbit.org, they give you some science experiments. You can follow Microbit EDU on the Educational Foundation on Twitter, and people are always posting great ways to use your microbits in your classroom, and other tips and tricks. And if you're struggling with something, reaching out over Twitter is typically a really great way to have crowdsource some solutions. If you want to put together this isn't, can't hold me to this price, but I would say it's roughly between $675 if you wanted to put together a kit for 25 to 30 students. So that would include 15 microbits, because remember, we're talking pair programming. So every student doesn't need to have a microbit. That would also automatically indicate that, you would do collaborative work when it came time to the project. You'd have, at least two, maybe more students working on the project together. The microbits, the version 2, I think you can get them around $18 and $19. So if you wanted to, double this. This was about $260 for that's wrong. It was like $360, I think, for the 15 microbits. So it would be, if you wanted to do 30 and have one microbit for each kid, that would be about $500 here. And so you'd have to add about 150 um, to $200 on here to, if you wanted to do that. It's $260 for on Amazon for to get the bundles for each student. It's about $260 um, and for 10. So figure that out. Uh, you'd need probably 200 alligator clips, and you're thinking that is a lot. But remember, each microbit has a minimum of 5 pins on it. And so students might be using the 3 volt. They're definitely going to be using the ground. They're going to be, using, they may program a whole bunch of different stuff. Uh, It's not unheard of for each project to have 10 to 15 microbits. So, I mean, alligator clips. So 200, you'd be surprised at how fast those get eaten up when you're doing a project. Um, I did 100 LED bulbs just because that's what you can buy as in the kit. Some of the, I won't go, extensively down through this whole thing, but these are the things that are probably a must have. Here's some optional things. The flex sensors can be a little expensive and they're a little fragile, so you want to be careful. I've spent a lot of money with flex sensors and replacing flex sensors, so cautionary tale there. I've already kind of talked about the servo motors. Um, and then you can get some inexpensive headphones that kids can hack into. I also I got a pizza place to donate some boxes for my secrets and safe projects. That's always good. And then typical maker space types of stuff, duct tape, masking tape, cardboard, all of these kinds of things that you might need for a particular project. And each project might have something, like if you're doing the plant watering, obviously you need a plant and some soil, and you need some sensors, which you can get soil sensors, but I believe that the project that they have on here, you can just use nails as the sensors. So think about $600 to $700 to do a classroom kit with the 15 microbits. Obviously, if you want one for each student, that's gonna add some significant more money in here. And these let me go back. These 3 resources right here are just like I use Amazon a lot. I would say I got almost all of this stuff on Amazon, except for the big kits. I couldn't get the big 10 microbit kits on Amazon, so I've got those they have them at any of these different places. This Chicago Electronic Distribution Center, which a teacher at Waterville Junior High, no, not Waterville, Winslow, turned me on to. This has great for a lot of different add-on little things that you can add on. So the microbit, when I talk about add-ons, and I'm sorry if I'm making you dizzy, but I am going to go back to the microbit itself here. So it has these 5 pins, but you can notice it also has these little lines. These are also pins, but it's really difficult to get to those. You can't get an alligator clip that's gonna get on to each one of these pins, but you can actually program these. Well, they have they have an extender board that you can do that extends out these pins in a way that you can actually connect them with alligator clips and other things. So they have those there. I saw like a little piano thing. Like I said, you can get soil sensors. There's stoplights. There's all kinds of different um, add-ons that Chicago Electronic distributors had. So I found them to be kind of a cool resource. And I'm going to go to the very end here. And so I hope that you got to know a little bit more about microbits, and that you are interested in getting started with physical computing. I will tell you that this is a highly engaging activity that you can do with students. There is a ton of problem solving involved in this, especially once they start hooking things up to their microbit. Uh, Usually, almost inevitably, every student I think I've ever had has reversed the positive and negative on the circuitry pieces and has been like, my micro, why isn't my light bulb lighting up? And then I'll be like, well, did you try the positive and changing those positive and negative? And then they're like, yeah, that works. So there's lots of iteration, there's lots of problem solving, collaborative work that students can do. So it's a highly engaging way to look at problem solving and bring in a little bit of computer science. So I like using them. I hope that you want to also give them a try in your classroom. And there, if you click on this, if you go to the PDF that's in the description of this video, and you go to the last slide in the slide deck and you click here, you can get 1 contact hour for watching this presentation. So I thank you again and have a great day.